In this lesson, we're going to cover Unit 6, Acquisition 3 on mass-to-mass conversions. So in these conversions, we're going to start with mass and we're going to end with mass. So why would this be important? Let's say we had a chemical reaction and we wanted to produce 5 grams of a product. And we needed to know how much of each reactant we would need. We could use stoichiometry to figure out the mass of each reactant needed to make a certain amount of product. Think of stoichiometry kind of like cooking. If you want to make 12 sandwiches and each sandwich has 2 pieces of bread, you can figure out how much bread you would need. Same thing with stoichiometry. If I need 12 grams of a product, how much of each reactant would I need? So first we're going to start by talking about mole ratios. A mole ratio is the ratio of 2 different substances involved in a chemical reaction. Ratio of 2 different substances involved in a chemical reaction. We are going to use mole ratio as a conversion factor. This is the conversion factor used when converting between moles of 2 different substances. And how do we know how many moles we have of a substance? The number of moles is going to be equal to the coefficient from the balanced reaction. So let's just start with a very simple mole ratio calculation before we get to a mass-to-mass. Let's say you were asked, how many moles of diatomic oxygen will be produced from 6.2 moles of water. And you'll be given the balanced reaction. Water decomposes into hydrogen plus oxygen. So the key that you need a mole ratio is we have 2 different substances. We are given water, but we're solving for oxygen. Anytime you're converting between 2 different substances, you need a mole ratio. It's kind of like comparing apples to oranges. We need a conversion factor to make sure we're comparing the correct substance. So just like all of our other conversions, always start with the given. So we are given 6.2 moles of H2O. So not only do we need the unit to cancel, moles goes in the denominator, but we also need the substance to cancel. So H2O goes into the denominator as well. Moles of H2O divided by moles of H2O are going to cancel out. Well, how do we figure out how many moles of water we have? It's equal to the coefficient from the balanced reaction. I have 2 moles of water. We are solving for moles of oxygen. whatever you're solving for will go in the numerator. Based on my balanced reaction, I just have 1 mole of oxygen. Multiply across the top, 6.2 times 1 is 6.2, divided by 2, 3.1 moles of oxygen. Moles of water divided by moles of water cancel out, and we are left with moles of oxygen. And again, this should make sense. For every 2 moles of water, we can only produce 1 mole of oxygen. I'm going to have half as much oxygen as I have water. So if I'm starting with 6.2 moles of water, it should make sense that we're only producing half as much oxygen. So now let's look at those mass-to-mass conversions. And I'm going to give you a little roadmap. We're going to start with mass. So let's say we're starting with grams. If you are given grams, the only thing that you can do is plug in the molar mass to solve for moles. Then we are going to convert from the given substance to what we're solving for using the mole ratio. Once we have moles of what we are solving for, we want to get back to mass. So again, just think about your conversion factors. If you have moles and we're solving for grams, the conversion factor is molar mass. All right, first problem. If 7.27 grams of ammonia react how many grams of water can be produced? And we have a balanced reaction. 4 moles of ammonia plus 3 moles of oxygen produces 2 moles of nitrogen plus 6 moles of water. So, just like any other conversion, whether it's 1-step, 2-step, 3-step, the process is always the same. Start with the given. We are given 7.27 grams NH3. Think about your conversion factors. If you're starting with grams, the only thing we can do is plug in molar mass to get to moles. Ammonia has a molar mass of 17.04 grams per mole. Since I'm starting with grams, grams goes in the denominator, so that unit cancels. 17.04 grams of ammonia in every 1 mole of ammonia. Grams divided by grams cancel, and now I'm at moles. I have moles of ammonia, but I'm solving for H2O. Anytime you are converting between 2 different substances, mole of one substance to mole of another, we need a mole ratio. Both the unit and the substance cancels. Always setting up the same unit on the diagonal. Grams to grams, moles of NH3 to moles of NH3. Based on my balanced reaction, I have 4 moles. Whatever you're solving for goes in the numerator. 6 moles H2O. Moles of NH3 divided by moles of NH3 cancels out. If we were to stop and solve, this would tell me how many moles of water we have, but I want to know how many grams of water we have. So last step, to go to moles of water to grams of water, we need the molar mass of water, which is 18.02 grams of water in every 1 mole of water. I know moles goes in the denominator because I need those units to cancel out. All right, let's put this in the calculator and see what we get. So we want to multiply everything across the top. I'm going to do this in one big calculation, so I'm going to use parentheses. 7.27 times 1 times 6 times 18.02 divided by what's on the bottom. 17.04 times 4 times 1, and my parenthesis, I get 11.532. We are always, always, always rounding our final answer to significant figures. The given has 3 sig figs, so my answer has 3 sig figs, and my units are grams of water. All right, let's try another one. How many grams of aluminum are required to produce 7.5 grams of aluminum chloride? And I'll give you the molar mass so we can save a little bit of time. So this is a mass-to-mass problem. We're starting with grams, we're ending with grams. So let's say we were actually doing this reaction in the lab, and we want to make 7.5 grams of aluminum chloride. Well, we would need to know how much aluminum we need to put into the reaction in order to produce those 7.5 grams. So we're always starting with the given. You should be writing the quantity, the units, and the substance. 7.5 grams aluminum chloride. Following our roadmap, if we're starting with grams, the first thing we're going to do is plug in the molar mass to get to moles. I'm starting with grams of aluminum chloride, so I'm going to use the molar mass of aluminum chloride. Always setting it up so our units cancel. So now I'm at moles of aluminum chloride, but I'm solving for just aluminum. I'm starting with a different substance that I'm solving for. Anytime you're converting between two different substances, you need a mole ratio. you need both the unit and the substance to cancel. We get the number of moles based on our coefficient from the balanced reaction. Whatever you're solving for goes in the numerator. I'm solving for aluminum, and there's 2 moles of aluminum. Moles of aluminum chloride divided by moles of aluminum chloride cancels out. Last step. If I want to go from moles of aluminum to grams of aluminum, I need the molar mass of aluminum. So this is an easy one. We can just look it up on the periodic table. Aluminum has a molar mass of 26.98 grams per every 1 mole. I know moles go in the denominator because I need it to cancel. You can also make your math easier. 2 divided by 2 is 1. We could simplify. So now I just multiply whatever is left across the top. 7.5 times 1, I canceled out this 2 times 26.98. Divided by 133.33. I canceled out this 2, and then that's just a 1, so we could ignore it. And I get 1.5176. My given has 2 significant figures, so I'll round my answer to 2 significant figures. And my units are grams of aluminum. All right, we're going to try to do one more quickly. If you are ready to try one on your own, once you copy down the problem, pause the video, try it on your own, see how you do. If 6.24 grams of oxygen reacts, how many grams of iron 3 oxide can be produced? So if you're ready to practice on your own, now's the time. Pause the video, come back and see how you did. If you need to walk through one more example with me, stick around. Always, always, always start with a given. You should be writing the quantity, the unit, and the substance. Automatically, you should be able to write your units. Whatever unit and substance you start with goes in the denominator, goes on the diagonal. So this has to be grams of O2. If I'm starting with grams, my conversion factor is the molar mass. Molar mass of oxygen is 32 grams per every 1 mole. Grams of oxygen divided by grams of oxygen cancel. So right now, if I were to stop and solve, this would give me moles of oxygen. But I need to get to iron 3 oxide. Anytime you're starting with a different substance than you're solving for, you need a mole ratio. We're going to go from mole to mole using the mole ratio. Again, this should be automatic. Whatever unit is here, write down here in the denominator. Based on my balanced reaction, 3 moles oxygen. Whatever you're solving for goes in the numerator. I'm solving for iron 3 oxide, 2 moles Fe2. O3. So again, moles of oxygen divided by moles of oxygen cancel. Units are automatic. This is moles of iron 3 oxide. This should be moles of iron 3 oxide. So I'm at moles, and I need to get to grams. Think of your conversion factor. The way that I convert from moles to grams is by plugging in the molar mass. 159.7 grams per every 1 mole. All right, let's multiply everything across the top. 6.24 times 1 times 2 times 159.7 divided by the bottom. 32 times 3 times 1. I get 20.761. The given has 3 significant figures, so my answer should have 3 significant figures. I would round this up to 20.8. Moles divided by moles cancel, and I'm left with grams of iron 3 oxide. So final answer, 20.8 grams, Fe2O3.